So I'd like to take my last lecture and discuss something a little more qualitative rather than quantitative, and that is experimental approaches to molecular communication. So what we're going to see is some ideas that researchers have come up with in designing actual molecular communication systems that work with not just with current technology, but with very simple, inexpensive technology that anyone can use. So the idea behind many of these experimental apparatus is that most engineers who start working on molecular communication do not have access to complicated apparatus. They don't have access to a wet lab, nor do they have expertise to use such equipment. So the idea is that molecular communication engineers have developed ways in which to start thinking about molecular communication and design apparatus and do experiments without access to any of that. What you'll see is that most of it is what I would call macro scale. In other words, while the idea of molecular communication is to perform communication at the nanoscale, most of the experimental apparatus that have been deployed so far are much larger. They would sit on a tabletop, for example. So why experiments? Experiments are critical for moving any new field forward, particularly so for molecular communication. One issue is that models are not as accurate or as well behaved in molecular communication as they are in wireless channels. And moreover, because of this, the models are not as widely accepted. So you can have, if you have 5 molecular communication papers, you could potentially have 5 different models. There's very little agreement on what constitutes the best models for analyzing molecular communication. What we need is the ground truth of experiments to tell us which models are correct and which are not. Implementations can reveal problems that are obscured by modeling assumptions. So when you model a system, theoretically, it's very easy to fall into the trap of making assumptions that simplify complex problems. And moreover, once you actually implement the system, you will encounter issues that you probably did not consider in your theoretical model, and you have to adapt to them and overcome them. Experience must be gained before tackling the visionary problems. So we have to, before we actually deploy nanoscale robots that are capable of interacting with human tissue at the cellular level, it's completely unreasonable to believe that we could do that correctly on the first try. We have to gain experience, and we have to understand the features of this new environment and this new way of communicating before we can ultimately go ahead and develop those applications. This is true of any field. The first rockets that went into space didn't go straight to the moon. There were many failures before we started to have success in space flight. More or less any technological endeavor, you will start with very simple implementations and move towards more complex ones as you gain actual real-world experimental experience. And finally, a very important reason for using experiments is that once you gain the experience of using molecular communication, even at the macro scale, it'll start opening up your eyes as far as new ideas are concerned for technologies and applications. And we'll look at that a little bit towards the end of this lecture. I want to talk first a bit about gaining experience. So again, this is what I was talking about. We have the visionary application of nanoscale robotics. In order to we have to start somewhere. We're not going to start here at the nanoscale. Where we're going to start is here with a very simple looking apparatus that sits on someone's desk in an office. There's nothing nanoscale about this. You can see the components. They're not terribly expensive. In fact, we'll talk about them. So we're gaining experience at this level so that someday in the future we can operate at this level. And what I want to talk about is this system that was developed in my lab. This is about 8 years ago now. And the idea, again, was I and my co-authors realized that we didn't have, we needed to gain experience with implementing molecular communication and seeing how it worked in practice in order to show people that this is a viable technique. And so without the availability of a wet lab, what we decided to do is we decided to do the simplest thing we could possibly think of. And what that was, if I come back to this figure for a second, we decided to send chemical messages encoded in alcohol vapor. So this device on the left over here is a spray gun. It's a motorized spray gun that can spray alcohol that's stored in this tank. And on the right-hand side, this over here is an alcohol sensor. So the idea is that messages are encoded in the concentration of alcohol and they're detected over here. Why did we do it this way? Because everything that you see here is very cheap. Alcohol sensors are very cheap. Spray devices for alcoholic solutions are cheap. There was nothing here that was terribly complicated to put together, and that's exactly what sold us on it. And what we ended up managing to do, again, about 8 years ago now, is we managed to send the world's first molecular communication text message, and this was it. So this is a figure from this paper, and what it shows is that we entered a text message. Here it's "O Canada." That's the first 2 words in the Canadian national anthem. On the right, it's too small to see, but if you go to the paper, you can see it. It's the output of the detector that shows that, in fact, we received the message correctly. Looking a little more closely, again, I want to emphasize that this system was very, very simple. There's nothing about this that was complicated. It was things that we just went out onto eBay or wherever and bought. We got off-the-shelf alcohol sensors. In fact, you can see on this board, there are 3 of them, and that's because we weren't sure which one was going to work the best. It turned out the MQ3 worked the best. This is a simple, basically home prototype circuit board that my student built. Anyone could do this. It's very simple to do once you know how. This is an Arduino. We also ordered some shields for the Arduino. Very easy to program. Nothing here, like I said, was terribly complicated, and it just sat on a table in my lab. And we proved that you could use it to send concentration shift key messages. And we also gained a huge amount of experience by understanding that the certain things that we assumed about the models of molecular communication up to that point weren't quite right. In particular, having to do with the intersymbol interference. The signals tended to be much more persistent than we thought they would be. So again, for tabletop molecular communication, the total cost of the apparatus you just saw was at most a few hundred Canadian dollars. It was mostly off-the-shelf devices and electronics. The parts that weren't off the shelf were homemade. They were very easy to make using kit parts, hobby kit parts. And the point that I want to make here is that you can do this anywhere. You can build this anywhere. You could do it, right? You could get excited about this, go home, order the parts, build something like this, and start doing molecular communication experiments as soon as you put it together. It's really not that complicated. And I encourage you to do it if you're interested. So this is about gaining experience. And part of gaining experience is improving your apparatus and doing new things with it. And this leads us to the new ideas for technologies that we can acquire from experimental approaches. The first thing that we managed to do, or the first idea we had, was why not take all this equipment that we have and put it on something mobile. So now we have an actual mobile device that can communicate with molecules. Our idea was that we would use it to read what I would call a barcode on a surface. So for instance, a series of dots, perhaps you could have a dot representing a 1 and no dot representing a 0. And if you drove the robot over the barcode, you could detect it. And this is an example of a result that we obtained. But all of the parts here, all the parts here are basically what you just saw before. It's just the the sensor. There's a couple of differences, including a microfan here, which is used to suck up the alcohol vapor. But you'll also notice that the robot, I'm actually not even sure if they sell these anymore, but at the time, this was about 5 years ago now, this was a Lego Mindstorms robot, which again, is just an off-the-shelf unit, very cheap. I'm sure you could get something something equivalent today. Very simple to build and use and program, and that's how we did it. So again, we were able to move beyond just a stationary transmitter and receiver. Now we have a mobile device, and the idea was that you could have these, we never quite got this far, but the idea was that you could have one robot leave a tag and the next robot read the tag. So you could have some sort of persistent communication that way. These ideas have been taken further. We've actually talked in this course about how, so here we have an idea for molecular MIMO. We talked about this a couple of classes ago. But we actually built a device. Actually, it was my collaborator in South Korea who built the device along with my former student, Nariman, who's now a professor. So congratulations to him. He did very well for molecular communication. And they built this MIMO device. It actually generated experimental results, and you can read a little more about it in this paper. I think I've mentioned this paper before. And it also got a write-up in IEEE Spectrum, and we were pretty pleased about that. Nariman has taken the ideas that we talked about considerably further. So again, further technologies, further experience. One of the things that we learned was that ISI is a major problem in these systems. So the persistence of an alcohol vapor, it just lasts for minutes, and it ends up being, the environment ends up getting saturated, and it's very hard to send information. So his idea was, what if we could get a chemical that canceled out another chemical? And his first obvious simple idea was to use pH. So he set up a liquid apparatus in which, if you want, I can't remember exactly how he did it, but it's something like, if you want to send a 0, you send an acid. If you want to send a 1, you send a base, and you can use those two symbols to cancel each other out. So the base will neutralize the acid, making ISI much easier to deal with. So again, experience that you gain through experiments will drive the theory and will drive the field forward. The first system that I showed you, it communicated at a rate of about 1 bit every 3 seconds, so 1/3 of a bit per second. But once we start getting into these kinds of devices, into MIMO and more complicated schemes, we're talking about an order of magnitude higher, so 3 bits per second. We're very far from what we believe the capacity of molecular communication is, even at these scales. But you can see that we are making significant progress, and it's all thanks to simple ideas and simple systems. I believe there's plenty of room for improvement as far as experimental apparatus in this sort of inexpensive domain is concerned. What's more is that these experimental apparatus give us new ideas for applications. So again, we were motivated. We were motivated by nanoscale applications. So our idea was that eventually these devices would go into the body and would perform therapeutic tasks at nanoscale dimensions. But as we developed these tabletop devices, we realized that in fact there are plenty of applications and plenty of potential commercial applications that can take place at the macro scale, at these larger scales. And here's some examples. So sewers, it turns out that sewers are very difficult to maintain. They're very leaky because it's very hard to tell what's going on down there. and it's obvious why. For one thing, they're not very pleasant places, and for another thing, they're basically metal tubes that are filled with salty water. So this is a terrible place for radio communication to occur. So this seems, however, this seems like a natural application for molecular communication. I mean, a sewer is something like a network of vessels, kind of like the bloodstream. I mean, it's very different in a lot of ways, but our ultimate goal is to get devices that function within the bloodstream. If you expand the concept of the bloodstream to much higher, much larger system, it could potentially look something like a sewer. So potentially you could design a molecular communication system with robots that autonomously explore sewers, exchanging information, searching for leaks, calling for help when necessary. This is something that goes well beyond any device that has been deployed so far. Another potential application, search and rescue. So this is an example, a sunken cruise ship. Imagine that there are survivors trapped somewhere within that ship. Again, and this is an extremely harsh environment for radio. Cruise ships are generally metal, especially if the victims are trapped on lower decks. It would be very difficult to get radio signals in there. And the hull would also be surrounded by salt water. So this is a tough environment for radio, and potentially an environment where, again, some robots that could search and could communicate using, coordinate and communicate using molecular communication could work quite well. Underground is another concept. So this is sort of related to the sewer idea. I chose this particular example, the Great Chicago Flood. This is something that happened in 1992. So it turns out that under Chicago, most of the major downtown buildings are connected by a series of tunnels. So in 1992, a construction accident caused these tunnels to start flooding, and no one knew where the water was coming from. There's no way to get down there, no way to get a signal out. Until they discovered by accident almost that it was a piling that had been driven through one of these tunnels under the river that was causing the problem. Instead, if you were wondering where flooding was come from, you could potentially send molecular communication robots down here in an environment that is, again, very harsh for radio. Taking this further, underground tunnels, one potential application would be in mining search and rescue. So mines are very difficult environments for radio, and potentially you could get these robots in a mine accident to search and try to find survivors. So more generally, this is a serious proposal for 6G, the next generation beyond 5G for wireless networks. So a key future goal of 6G networks is to provide ubiquitous connectivity for Internet of Things applications. So ubiquitous means everywhere. And what we have seen in some of these technological and applicational examples is that many important applications are what I would call what people would call wave denied. Which is to say that EM waves are awkward, or they can't propagate, or they're difficult to deal with, or it's generally a very harsh environment for radio. So these are important applications. They need to connect to networks, particularly for ubiquitous Internet of Things applications. There's very important commercial reasons why you would want to keep tabs on what's happening in sewers, for example, or mines, even though these are not great environments for radio. So potentially molecular communication offers a solution. There's this very recent paper, it just appeared in IEEE Communications magazine, that actually describes some of these potential applications and lays out a very concise and interesting proposal for adding molecular communication to 6G standards. So I think the future is very bright for molecular communication. I think there's lots of potential interesting applications that could be performed. And the point that I want to get across to you is that you could go home today, order some of this equipment, put something together, and potentially start a business based on molecular communication that solves some of these problems and moves us into a new technological paradigm for wave-denied communication environments. And with that, I would like to conclude this short course. Thank you very much to all of you who have listened to my lectures. Thank you to Professor Banerjee and the organizing committee for making this possible. I want to thank everyone who helped make this happen. It is indeed a great regret that I was not able to come and see you in person in India. I was actually very much looking forward to it last year, but perhaps sometime in the future, I will be able to find an opportunity to come to India and visit you all in person very soon. With that, my lab website is here. My email address is here. I would very much love to hear from you, any comments or questions that you might have. And that's all I have to say. So thank you very much for your attention.